People are often quite surprised when they learn that hydraulic fracturing, or fracking as it's colloquially known, has been commonplace in the UK North Sea for 50 years. It is a surprisingly precise and subtle process when properly controlled and managed. However, if we were to go over to America in the 1960s, it feels like an eternity ago now, but I used to work in the oil and gas industry. I was a drilling engineer. It's something I've mentioned in the past and I've been asked many times to make a video about it, but I never really wanted to. The thing is, most of what I worked on just seems really boring to me. I suppose I could talk about the Troll Alpha, or the 40s subsea pipeline, or I could make the billionth video about the Byford Dolphin incident, but I try to do topics that haven't been covered a billion times already. 6 months ago, Paul Shadison released a follow-up to the best sci-fi show I've ever seen, Solstice 5. If you haven't seen it, just pause my video right now, hit the link at the top right of this one. Paul presents us with a dystopia, free of Earth's ethical constraints. A real-life Factorio where resource extraction must grow at any cost. The most efficient, the most destructive method of deep resource extraction, presented, is nuclear fracking. Something that could never happen on Earth. Thing is, nuclear fracking isn't sci-fi. It's happened. Many times. It is certainly destructive, but it may be the least efficient form of resource extraction ever attempted. It is also quite possibly the most ridiculous non-combative thing humans have ever done. Alright, before we start dropping nuclear warheads down gas wells, I need to explain how a gas well is constructed. I used to design oil wells in the North Sea. These were generally bigger and more productive than onshore wells, and, well, they produce mainly oil. But the design is essentially the same. What I used to work on was just bigger and 100 miles offshore. I'll mainly be focusing on the drilling engineering side of things in this video, rather than the whole how a nuke works side of things. That way, hopefully, that gentleman who is an actual nuclear engineer won't see this and point out every time I'm an idiot. I'll also struggle for visuals in this video, since basically everything I'm discussing happened underground. I have some public domain footage of the operations which I'll be using and annotating throughout. I'll animate what I can, and I may include some footage of offshore drilling hardware from around where I live. It's much larger than the onshore kit used in the operations discussed, but hopefully it can give some context. Alright, so it turned out the day before I released this video, there was a big offshore energy conference in Aberdeen, so I went along with the view to try and film some equipment. I did film some equipment, and it'll be annotated throughout this video, but I actually spent most of the time filming all the cool model boats that some of the exhibitors had on display. Since I couldn't make any models for this video, I think that fits in quite nicely, so enjoy those, I suppose, as well. Why does a well need designing? It's just a hole in the ground. Is a question I have been asked many times. Here is our rig on the surface. Here is our gas reservoir. Let's just drill a hole into the ground then. Okay, to do that we'll need to circulate fluid down the drill pipe and back up the wellbore to carry the cuttings back to surface. Let's think about that fluid. Here's a plot of fluid pressure in the rocks with depth, with the reservoir being at higher pressure than the formation immediately above it. When we drill into that reservoir, we need to make sure the pressure in our hole is higher than the reservoir pressure. So we choose a drilling fluid of high enough density to stop gas flowing into the well, but not too high or it'll fracture the rock. It's not quite time for that yet. Oh, and by the way, that fluid's colloquially called drilling mud. It's basically just water and bentonite. Add more bentonite to increase the density. You can add a lot of other chemicals too for other purposes if you desire. We'll get back to that later. And just by thinking about the basics of our drilling fluid, we've already done some basic well design. So yeah, it's not just a hole in the ground. Okay, so we've got sufficient wellbore pressure. Let's drill the reservoir section. Okay, now what? We can't just let gas flow into the wellbore, it'd rush up and blow out the top. We need to somehow add a valve to the top to control the gas flow. We need to replace the fluid in the well for a lighter fluid to let the gas flow in. So we run casing, like this, and circulate cement to hold it in place. Well, the reservoir's sealed off again now, so run a string of shaped explosive charges to the reservoir section. these perforating charges blow holes in the casing to let gas flow in. None'll flow in yet though, remember the drilling fluid's stopping that. We run tubing for the gas to flow to the surface through, like this, attach some valves to the top and open them to flow the gas out. In reality, we have multiple casing strings like this, and the well's likely to be deviated. I've simplified basically everything except what we need to know for this video, but we have a gas well. How can we make it more profitable? All that drilling and forcing drilling fluid into the rock damages the outer surface of the wellbore. This restricts flow of gas into the well. A secondary advantage of those perforating charges is that they tend to blow past that skin damage and help the gas flow in more easily. Perforating charges are often able to blow more than a metre into the rock. Naturally, they can, and have, cut people in half if detonated prematurely. Explosives are used a lot in the oil and gas industry. They are really dangerous, but from my experience, they're managed incredibly well. From memory, the procedures for dealing with explosives universally included switching off all radio equipment on the rig to minimise the risk of a stray signal causing an accidental detonation. All boats would be evacuated to a safe zone a given distance away, just in case a charge went off in the riser. A dedicated crew member went up the derrick to visually look for lightning, again just to minimise the chance of something setting things off. And explosives were stored on a jettisonable platform that could be dumped overboard in the case of an emergency. The amount of paperwork and process to use explosives made the entire process boring and laborious, and that was by design. I mentioned in an earlier video that we preferred to use what was essentially a tripropellant rocket engine in a different form factor, which used horrifyingly hazardous chemicals to blast out white-hot jets of exhaust instead of explosives where possible. I really want to get that point across here. Explosives are by far the most hazardous thing used in a drilling operation. Since about the 1930s, American gas drillers realised they could dump as much nitroglycerin down oil wells as possible and detonate it. This was before the days of perforating charges, where reservoir sections would be drilled out as an open hole. The explosion would fracture the reservoir formation and in some cases allow for measurable increases in gas production. It was a crude and unpredictable method, but often worked to an extent. Just to be clear, when I say reservoir formation, I mean rock, usually sandstone, which contains gas in the pores between the rock grains. Fracturing that rock increases its overall permeability and lets more gas flow into the well. If you've seen my full video on the tripropellant rocket, you may think that was one of the most dangerous ideas ever executed. I have a lot of comments on that video declaring the idea as stupid and reckless. Or you may think blowing up large quantities of nitroglycerin sounds worse. Oh, we've seen nothing. That is nothing compared to what we're about to talk about. At any given time, the world is full of problems without apparent solutions. Sometimes, however, it's fun to focus on the opposite, solutions without problems. Something like, I don't know, a blockchain. Very, very clever, but pretty much useless save for a few niche cases. Nuclear weapons, on the other hand, well, they're just a problem. The US had more than 30,000 of the damn things by the mid-1960s. Maybe they could be used for something other than ending the world.
Some days you just can't get rid of a bomb.
And that is how the legendary Project Plowshare was born. Peaceful use of nuclear weapons is quite the concept, and nuclear fracking was the application that was advanced the furthest. We'll talk about Plowshare's most unhinged proposal at the end of this video. As ridiculous as everything we're about to talk about is, nuclear fracking was also probably the least ridiculous concept explained by Plowshare. Let's draw a nice graph to put things into context. We just tried to frack a well with nitroglycerin. Here is the energy of nitroglycerin. That is the amount of energy released when a pound of it is burned. Okay, why is SI units Alex using pounds now? I'm going to keep the unhinged factor up by using not US standard units, but oil field units throughout this video. If you aren't aware of oil field units, I'm probably going to be making up a follow-up video to this explaining them. They make US standard units look orderly and logical by comparison. Okay, I know it's not actually directly comparable because nitroglycerin included the oxidizer. Trust me, it's not going to matter. Here's a pound of natural gas. Weird to express that by mass, I know, but again, don't worry about it. Because now, let's look at the energy density of uranium-235. Oh. And just to be clear, there are different ways of defining energy density for nuclear reactions. That could be uranium-235 in different types of reactor, undergoing different types of decay, or whatever. And if you use it in a bomb, you don't get anywhere near 100% energy conversion. But I don't think it really matters if our line goes to Dundee, Edinburgh, Glasgow, whatever. You get the point. Now, just imagine how hard we could frack a well if we used a nuke instead of nitroglycerin. Imagine the value we could deliver to our shareholders. There are 6 countries in the world that have nuked themselves. If you want to test out your nukes, you kind of have to do that. Or you could nuke a friend, or nuke the whales, or nuke space, or nuke paradise. Of those 6, 2 have nuked themselves for commercial reasons. Let's begin with the first time the US did that. I'll be using the various design documents and post-work evaluation reports to piece together the next few chapters. I'm still pretty fluent in well-designed documents, and honestly, some of them look basically identical to the ones I used to read on a daily basis for North Sea oil wells. Any well report will frequently refer to downhole tools as just tools or devices. The reports we'll be studying do exactly the same, except every now and then the device in question is an atomic bomb. So let's look at the feasibility report for the US's first nuclear fracking operation, Project Gasbuggy. A lot of you probably already have something in mind for the nuclear device. We definitely don't want something too big, but the concept of a small nuke is generally something of an oxymoron. The weapons that obliterated Hiroshima and Nagasaki were very much small in comparison to the veritable pick and mix available to the US in the 1960s. So, I bet many of you are picturing one of these, a Davy Crockett bomb. This is probably the only nuke put into service that I'd call small. It looked kind of adorable and had a yield of about 15 tons of TNT. For the record, that's about the same as the current largest airdropped conventional bomb in the US arsenal. Certainly a lot more dangerous than conventional explosives, but I reckon we could justify a measly 15-ton explosion downhole. Well, the proposal was actually for a 10-kiloton bomb. Keep that number in the back of your mind, it's gonna change. Prior to Gasbuggy, the hard hat test in 1962 saw a 5-kiloton device detonated underground. Subsequent boreholes drilled into the surrounding rock were pressurized with air and the leak-off rate measured to determine permeability. The fractured rock a few hundred feet from the detonation center exhibited about 2 orders of magnitude higher permeability than before the blast. Gasbuggy sought to replicate these results, but in a gas-bearing reservoir. The test site was here, high in the hills of New Mexico, and, of course, right on the edge of a Native American reserve. The target formation was a gas-bearing sandstone layer about 300 feet thick and about 4,000 feet below the surface. An existing well just 600 feet from the site had been producing gas from this formation for several years prior, so would function as a good performance comparison. On the subject of the existing well, who was actually doing all of this? Gasbuggy was a private-public collaboration between the US Atomic Energy Commission, who'd be supplying the nuke, and the El Paso Natural Gas Company. Of course, this is a great setup, as if there's one market sector that could be trusted with nuclear weapons, it is definitely private oil and gas companies. Anyway, I particularly like this little tidbit from the feasibility study assessing the cost of a nuke. Quote, "The latest information made available by the Atomic Energy Commission is that the projected charges for nuclear explosives will range from $350,000 for yields of about 10 kilotons to $600,000 for yields of 2 megatons." End quote. Converting to today's money, that's about $3.5 million and $6 million respectively. I have two immediate thoughts here. Number one, nukes are apparently a lot cheaper than I thought. Or they were in the 60s anyway. For the price of a large house in a major city, you can wipe said city off the map. Number two, look at the value for large nukes. I presume there's a fixed cost for building any size of warhead, but based on the two data points here, once you've got all that in place, increasing the yield is proportionally cheap, so buy big. I think this is one of these points in the video where it's good to stop and remind ourselves how balls to the wall insane it is to have a preliminary cost analysis of an atomic bomb in a drilling study. Anyway, next is the small matter of building a device that can actually fit down a gas well. Well casing comes in standard sizes. The production casing I showed in this diagram tends to be 9 5/8 of an inch in external diameter, and if a production line is used, that tends to be about 7 inches. Of course, well diameters can vary wildly, but today we'll generally be dealing with 9 5/8 inch casing. When accounting for wall thickness, that would leave there about 7 inches for a device. And that device would be built by Lawrence Livermore National Lab. Everything we will deal with today will involve fission-only devices. To the best of my knowledge, nobody's tried to frack a well with a fusion bomb yet. So, the bomb, I'm just going to start calling it a bomb rather than a device or a charge or whatever. The bomb would be run into the drilled hole, which would be filled with cement to entomb it before it was detonated. The prediction was that this would almost instantaneously vaporize, melt, and generally make a colossal mess of all the rock within about 100 feet. The resulting chamber would then collapse along with much of the rock above. This would form a rubble chimney through which the gas would flow upwards. Surrounding this chimney would be a fractured zone out to some 400 feet or so. The rubble chimney would be drilled into. You may spot a massive issue with that if you were paying attention earlier. Completion tubing run to a wellhead on the surface and the gas allowed to flow. Now, that massive issue is not radioactive contamination. That is a separate massive issue. But luckily, the feasibility study devoted a whole 2 pages to addressing this. Those 2 pages are best summarised as fission byproducts decay relatively quickly, so wait a while before flowing the gas to surface. Which, of course, is correct to an extent. It is the reason Hiroshima isn't a radioactive wasteland now, but let's come back to that later. It's also explicitly stated that exactly what fission products and how much of them would be produced was essentially unknown. Again, to put this into perspective, one of the absolute nightmare scenarios back when I worked in the industry was accidentally drilling into a radioactive source. If you can think of something hazardous, it is probably run down oil wells frequently. Radioactive sources are used in some of the well logging tools, for instance those used to measure rock porosity, and those sources are extremely active. We're not talking about that little flea in your smoke alarm here, we're talking about Guyana accident scale and up. These can, and very rarely do, get stuck down hole, and if they can't be retrieved, the only option is to abandon them down there. This would involve a lot of paperwork and then entombing them in cement which was dyed green. If somehow someone screwed up and tried to re-drill the well, hopefully they'd see the green cement in the return fluid, and if that all failed, all rigs have radiation detectors monitoring the returning fluid for radioactive contamination. Mainly for naturally occurring radioactive minerals in the cuttings, but if a man-made source was somehow accidentally breached and made its way into the wellbore, everyone would know about it. Every truck in and out of our stockyard had to pass through a radiation detector too, just in case something somehow got loose and made its way back to the shore. So, the prospect of intentionally drilling into a known radioactive zone certainly gets my attention. Yeah, it's not going to hit material as active as something I just described, or at least I don't think it would, but still, I'd recommend against it. Natural decay aside, the feasibility study for Gasbuggy predicted that the unfissioned uranium and the heavier daughter products would be entombed at the bottom of the chimney in glass, which solidified from the molten rock. Alright, let's see how that all went. By 1967, the US Atomic Energy Commission was ready. The El Paso Natural Gas Company were ready. Lawrence Livermore National Lab had delivered the bomb. In fact, they over-delivered. It wasn't a 10 kiloton bomb, it was 29 kilotons, or about 2 Hiroshimas. Here it is. I can't tell you a huge amount about it because not much has been published, but I think it suffices to know it was a 29 kiloton fission bomb in a 7-inch canister. It contained all the necessary control and monitoring electronics to not only detonate the bomb when the time came, but also to ensure the environment was within acceptable parameters, namely the pressure and temperature. The temperature control appears to be that of the greatest concern. Bottom hole temperatures for Gasbuggy were 131 degrees Fahrenheit, which is a very low temperature for a hydrocarbon well in my experience. Remember, North Sea wells are generally about 3 times that depth and 10 times the complexity of what we're dealing with here. Nevertheless, the explosive canister contained active refrigeration units to maintain a temperature below 100 degrees Fahrenheit, the max operating temperature for the nuke. It's probably worth noting, I'm pretty sure this would be impossible even today for the kinds of wells I worked on, which were typically above 300 Fahrenheit at reservoir. I don't think you could possibly dissipate that kind of heat for an extended period of time downhole without pumping refrigerant from surface. Anyway, the power needed to run the refrigeration and to control and monitor the bomb was provided by this armoured cable. Nothing unusual there, except if that cable was somehow cut or damaged, the crew would be left with an uncontrolled nuclear bomb at an undetermined depth downhole. For reference, this looks just like any other downhole tool. I suppose it kind of looks like a rocket if you don't know what you're looking at, but if you asked me without context, I'd have guessed it was a downhole safety valve, not an atomic bomb. You can see the control cable being fed into it here. In the case of Gasbuggy, the 7-inch diameter constraint turned out not to be necessary. We'll get to why in a second, but it's obvious that the device was actually closer to 10 inches in diameter from these photos. Oh, and remember how I mentioned safety procedures for conventional explosives? The first one of those was that everyone non-essential would evacuate the rig floor when explosives were at surface. Usually, you'd just have an explosive specialist, a driller, and the minimum number of roughnecks to run them in. In fact, when the charges are being armed, the specialist is normally the only person on the drill floor. Apparently that doesn't apply with nukes. Look at everyone here just chilling, living in the moment. The emplacement well itself was a bit odd in terms of gas wells, in that it was pretty much the oversimplified hole in the ground I walked us through in the intro. A 13 3/4 inch hole was drilled to depth and then reamed out to 28 inches. Not only is this a huge wellbore diameter for a hydrocarbon well, but running a single hole section from surface like this is unusual. The hole was cased off with 24-inch casing. Prior to drilling the emplacement well, a more conventional well was drilled 188 feet away to assess the in-situ permeability and flow rate. A second monitoring well was drilled 302 feet away before being temporarily plugged with cement. This would be used for flow testing after the detonation. Both of these wells are seen here. They look far more conventional, with 9 5/8 and 7-inch casing at the reservoir respectively. The bomb was pre-armed and run to the bottom of the emplacement well. Some problems were encountered, of course. The cold weather apparently hampered drilling operations, and the downhole refrigeration unit behaved sporadically at points, partially failing with the bomb at depth. But operations proceeded, and the device was cemented in place, with cement pumped all the way back to surface. On the 10th of December 1967, the immediate area was evacuated. A bunch of VIPs gathered in a marquee for some reason, and the US entered the Nuclear Fracking Club. As I gather, there was no excessive ground movement. There's a video floating around of a cow being startled by an underground nuke, but I suspect that's from one of the earlier, shallower tests, not from Gasbuggy. To the credit of everyone involved, extensive radioactive monitoring sensors were installed around the site and down both of the monitoring wells. A small team of monitoring crew were sent in to confirm the site was clear of contamination, then the drill crew were brought back to drill the well. Again. Contrary to my suggested approach from earlier of maybe waiting a while to let the most active fission products decay, re-entry began 3 days after the detonation. Upon approaching the newly created rubble chimney, circulation of the drilling fluid was lost. That's the massive issue I'd hinted at earlier. Normally, that would be a pretty hairy situation in a conventional well. There are a bunch of solutions to lost circulation. My favourite is to pump shredded up mica down the well to hopefully plug up the formation. Hit a reservoir while taking losses and you risk a blowout. And remember, that blowout will be radioactive in this case. The crew were clearly prepared for this, though. The drilling report doesn't actually state how they dealt with it, bar the sentence, "drilling continued without circulation." which makes me profoundly uncomfortable. Soon after, the bit started encountering voids in the rock. So the bottom was called on January 10th, 1968. The drill string was retrieved and completion tubing run and tied to production valves at the top. So, did it work? Of course it didn't. The gas was radioactive. The feasibility study was quite clear and honest that the level of radioactivity expected in the produced gas was largely unknown. The downhole chemistry and how it would interact with the neutron stream from the detonation was complex and poorly understood at the time. The two major radioactive byproducts expected in the produced gas were krypton-85 and tritium, but the observed quantity of tritium was far higher than expected. The production report estimates about 45,000 curies of tritium were present in the rubble chimney immediately after the blast. I should jump in here and make clear, the atmospheric releases weren't awful. This vial of tritium contains about 1/20th of a curie, so although all these experiments would have created a huge amount of radioactive byproducts, the majority of them did stay underground. Now, the well was flowed periodically for a couple of years, and the activity was seen to decrease significantly, down to about 50 picocuries per cubic centimetre of gas. Horrible unit there, by the way. It would be becquerels per cubic metre if I was using SI. So, about 18,500 becquerels per cubic metre after 2 years. I can't really get a straight answer on what the max permitted radioactivity of natural gas is for it to be sold, but it seems to be somewhere around 500 becquerels per cubic metre. So after 2 years, the gas from Gasbuggy was about 37 times more radioactive than permitted for sale. Oh, and during those flow tests, the gas was flared. That would release the radioactive products to the atmosphere. No real word on how much was released to atmosphere. One preliminary report says, quote, "The amount of radioactivity released to the atmosphere is one of the questions being studied," end quote. Doesn't really fill me with confidence. As with any hydrocarbon well, a fraction of the produced fluid was water. But in this case, tritiated. That is I struggle to say that, don't I? In this case, tritiated. I can't say it like that either. I'll just say it normally. In this case, tritiated water. Ooh, I'm going to get a lot of comments about that, aren't I? No word on how tritiated it was, but it was stored in a large tank and injected into the flare for, quote, disposal, end quote. It stated that there were, quote, no hazards to any personnel involved from this, end quote. For what it's worth, Gasbuggy was a long way from any built-up areas, and I presume the radioactivity was sufficiently diluted in the atmosphere to not cause any long-term problems. Okay, so let's just put aside the awkward problem of radioactive contamination. Take a 1960s approach and just ignore it for now. How much extra gas did the well produce? Well, first of all, for the first few days, 36% of that gas was carbon dioxide. This was far higher than anticipated and was thought to originate from the vaporization of the rock. For the record, CO2 absolutely shreds production tubing unless you use expensive high chromium steel. As for the natural gas, by measuring flow between the emplacement and monitoring wells, the permeability was estimated to increase about 5-fold to around 8 millidarcies near the rubble chimney, dropping off rapidly. At 250 feet from the well, we're looking at a permeability of less than 0.05 millidarcies. The team had anticipated more than 100 millidarcies, so this was a disappointment. What is a millidarcy? It's one of the many cursed oil field units, but for context, about 10 millidarcies was typical for the reservoirs I used to work on. But an increase is an increase. And remember, this is a gas well, so much lower permeabilities are typical. How much extra gas did it produce? About 5 times as much as the existing nearest well, and about 8 times as much as the average of the 5 nearest wells in the field. The Gasbuggy emplacement well was the highest producer in the field during the flow tests, and would have produced an estimated 900 million cubic feet of gas if left to produce for 20 years. Quick note, 1 cubic foot of gas isn't much. Although that number sounds huge, it's not remarkable for a gas well. But this does sound pretty fantastic. Of course, there's a big old caveat. Remember how I focused on the unusually large diameter of the Gasbuggy emplacement well? Generally, the higher the diameter, the higher the gas flow. A 5 times increase in flow rate is about what we'd expect to see through 20-inch casing compared to 9 and 5/8-inch casing. So, while the addition of an atomic bomb turned a significant proportion of the gas into carbon dioxide and made it radioactive, it's impossible to categorically determine whether it actually increased the production at all. I sound a bit like one of those weird SpaceX people now, but at least they got good data. And indeed they did. The post-shot reports are quick to point out that despite the disappointing permeability results and ambiguous flow, the fact it was shown nuclear fracking could even be carried out safely at all was considered a success. The USGS were happy with the news, and their models regarding chimney size and fracture extent were validated. So who knows? If anyone ever needs to detonate a nuke far underground again, we know what'll happen. But all that aside, with the failure to demonstrate commercial viability, the team packed up and called it a day, and bigger bomb! The solution was clearly a bigger bomb. Project Rulison was the second attempt to fracture a well with an atomic bomb. And spoiler, this one was the most successful of all the US tests. The objective this time wasn't just to prove it was possible to fracture a reservoir, but to demonstrate commercial feasibility. Now, we aren't talking that much bigger. Gasbuggy's blast was 2 Hiroshimas. Rulison's was closer to 3 Hiroshimas. This time we're in Colorado, near the district of Rifle, just to make things that bit more American. And the detonation occurred on September the 10th, 1969, at 3 p.m. I know it was 3 p.m. because the drilling report specifically states this time was chosen to detonate a 45 kiloton atomic bomb after considering a few factors which included the work schedule of local underground mine workers, the traffic frequency of the Denver and Rio Grande Western Railroad, and the local school bus schedule. Carried out this time in conjunction with the Austral Drilling Company, a different emplacement method was used for the bomb. So let's take a look at the setup. As with Gasbuggy, an emplacement hole was drilled and the bomb inserted into the reservoir section. Rulison was much deeper at around 8,200 feet bottom hole depth. The bomb was about 9 inches in diameter and plenty of video of it survives. It was run on the armoured cable rather than on the casing. Once placed, the bomb was cemented in place as before. The bottom hole temperature was much higher than Gasbuggy, at around 430 degrees Fahrenheit. I'm not exactly sure how that was managed, but I presume the bomb and all its associated electronics were just built to handle that kind of high temperature this time. As with Gasbuggy, details on the device itself are very sparse, with the device being an atomic bomb and all. Prior to all this, an exploration well was drilled and used to measure gas flow before the detonation. It was plugged back and then sidetracked after the detonation occurred. This is a common practice, particularly with offshore wells where there's limited slots on a platform to drill from. A depleted well can be sidetracked into a more productive area of the reservoir. In this case, it was sidetracked into the newly formed rubble chimney, which was estimated to be about 250 feet in height, with a fracture zone extending about 400 feet from the blast centre. Let's just pause a second here. This is maybe outside the scope of this video, but it's worth addressing. I normally release these videos a few days early on Patreon. In this case, I got a bunch of questions here. How on earth do you steer a drill bit around kilometres below the surface? It's easy for me to forget the scale and complexity of drilling operations. I used to take this stuff for granted. So, a very quick explanation on directional drilling. The key factor to remember is the scale of these wells. The drill pipe is basically as flexible as spaghetti at this scale, so it can trace out a curve no problem. To do this back in the 1970s, an assembly called a mud motor would be run into the hole when they wanted to drill a curved section. This was on the end of an angled piece of pipe called a bent sub. The mud motor is a turbine driven by the drilling fluid that's pumped down the drill pipe. It rotates and turns the bit without the drill string being turned. So, a curved section could be drilled with this mud motor, which was then run back out of the hole, replaced with a conventional drill bit, and the next straight section drilled. Today, this is done with something called a rotary steerable system, which honestly makes directional drilling trivial from a well engineer's perspective. Rotary steerable systems are far too complex to discuss in detail now, but let's just say they're the reason that more than half of my videos to date talk about inertial guidance systems at some point. Crucially, the team waited 7 months to drill the sidetracked appraisal well. The drilling report states this allowed the radioactivity to decay to 1,000th of that present after the detonation. I'm not sure how they arrived at that figure, since tritium has a half-life of 10 years, but perhaps they were referring to the other fission products from the blast. Using the same well for pre- and post-shot testing would have no doubt complicated operations, but allowed for comparable tests to be formed to accurately determine the improvement in production. So what was the increase? Let's do gas volume first. In 108 days, the appraisal well produced the same volume of gas as a typical well in the field would in about 10 years. The permeability of the rocks surrounding the blast increased 33-fold out to a radius of 2.75 that of the chimney. It was estimated that the well would produce between 1.8 and 4.5 billion cubic feet if left to flow for 20 years. Rullison positively demonstrated that detonating an atomic bomb down a gas well will absolutely give a huge increase in gas production if done correctly. Of course, this is putting aside those niggling factors like the produced gas being radioactive and the safety challenges of handing nukes over to a bunch of roughnecks. As for the radioactivity of the gas, well, not great, but not terrible. Actually, no, it was still pretty terrible. But a significant improvement over Gasbuggy. About 10,000 curies total were estimated to be present in the chimney after detonation. Less than a quarter of that seen in Gasbuggy, and from a larger blast and a much larger volume of produced gas. After 180 days of production, the activity in the gas had fallen to about 0.2 microcuries per cubic foot, or about 250,000 becquerels per cubic meter. The trend was continuing downwards, so I'm pretty confident it would have exhibited less radioactivity than the Gasbuggy gas if flow testing were carried out over the same 2-year period. But still far too radioactive to be sold. However we go about it, any radioactivity tied up in the produced fluid had to be released to atmosphere while the chimney region was cleared. The lower overall radioactivity of Rullison was assumed to be due to 2 factors. The first was a more complete detonation, melting rock around the chimney more thoroughly and trapping the harmful isotopes in the glass. The second, and probably more significant, was due to the use of granules of boron carbide around the detonation zone. Shown here in the well diagram, a sleeve was welded to the outside of the casing which contained the boron carbide. As you probably know, boron absorbs neutrons. I'm sure this is a very simplified view, but the sleeve would have absorbed much of the neutron activity from the blast, preventing it from interacting with the hydrogen in the formation water to form tritium. But even with the high flow rate, it was clearly evident that the radioactivity issue precluded the production of a commercial product. So the team decided to call multiple nukes. The next attempt used 3 nukes at once. I'll keep this one brief because I think this is the point where the US Atomic Energy Commission really jumped the shark on nuclear fracking. Also, we're now at 1973 and the general public had started to figure out what was going on, and it seems the various participants were a little less keen to openly publish their results. Rio Blanco detonated a total of 6.5 Hiroshimas in the form of 3 33-kiloton bombs, detonated simultaneously around 6,000 foot under Colorado. The idea was to create 3 separate rubble chimneys through a thick section of reservoir. Those 3 chimneys would be in hydraulic communication, with the gas able to percolate through all 3 and up to the wellbore. Let's start with the good news. The total radioactivity in the produced section of the well was estimated to be 1,000 curies. That is 1/10 of that of Rullison. In all honesty, pretty great result. But the total volume of gas produced was underwhelming. About 98 million cubic feet over a period of a few weeks, despite the reservoir section being far thicker than the previous tests, and the blast energy being more than double that of Rullison. Well, the reason for this turned out to be a lack of communication between the top and lower 2 rubble chimneys. The well was only producing meaningful amounts of gas from the fractured zone resulting from the top detonation. All that melted rock had solidified into radioactive glass. It pooled at the bottom of each chimney, exactly as predicted, but cut off upward flow from below. For the cost of 3 atomic bombs, a complex drilling campaign, and a difficult subsurface detonation operation, Rio Blanco in effect created a gas well on top of 2 partially plugged gas wells. So finally it was time to more nukes, and much bigger. 5 nukes, 100 kilotons each, for a total of 32 Hiroshimas, 10,000 foot under the surface of Wyoming. Oh, and by the way, they had to be exploded sequentially. A simultaneous detonation would contravene the Threshold Test Ban Treaty, which forbade tests above 150 kilotons in size. Except this never happened. By 1973, public opposition to anything nuclear was accelerating. Yes, that would have absolutely dire consequences for how we produce electricity in the coming decades, but, and I can't stress this enough, a nuclear bomb is not a nuclear power station. In this case, though, I think we can all agree the opposition was well placed. When both the local public and various politicians in Washington got hold of the plan, it was stopped in its tracks. Rio Blanco was the last time the US ever tried to frack a well with a nuclear bomb. So, let's summarise all the major problems with nuclear fracking. We've obviously discussed the radioactivity and the unpredictability, but there's something more fundamental. As I've alluded to many times now, a buried nuclear detonation delivers a huge amount of energy to the surrounding rock, and that energy release is essentially uncontrolled. The hope for nuclear fracking was that enough of that energy would be mechanical and would go into fracturing the rock. But of course, much of it instead went into vaporising and melting the rock, completely wasting it. In fact, in the case of Rio Blanco, worse than wasting it, that melted rock actively hindered the gas flow. If we lived in some alternative universe where we invented the atom bomb but not the nuclear reactor, maybe we'd still create nuclear power plants. We could detonate nukes in emplacement holes and inject water into the hot rock, turning it into steam to drive a turbine. That's a daft prospect, but it does raise a very serious question. Remember the big graph from earlier? Couldn't be, could it? Was the energy delivered by the detonations more than the energy of the extracted gas? Okay, here are my calculations on screen. We'll assume the wells would have flowed over a 20-year lifetime as estimated in the project reports. Well, it's not quite a negative energy balance, but it's hardly a great picture. The detonation for Rullison equaled 1/10 of all the gas that could be extracted from that well over a 20-year period. And had Wagon Wheel gone ahead, the energy put into fracturing may have actually been about equal to that of all the gas extracted. Wouldn't it just be easier to make fuel rods from the uranium and use them in a nuclear reactor? And of course the answer to that is yes. Just the act of making an atomic bomb is wildly more difficult than making a fuel rod, with enrichment to something like 90% of uranium-235 required in that case of a bomb. Nuclear fuel rods are only enriched to something like 3.5% U-235. So there you go. From an energy perspective, nuclear fracking is essentially a complete waste of time, a complete waste of energy, and therefore, in my opinion, quite possibly the most inefficient means of resource extraction ever attempted. Now let's see how it's done properly. About 10 years ago, hydraulic fracturing, or fracking as it's almost universally referred to now, was a highly political topic. I actually wrote an entire chapter going over my opinion on all of this, and then realised I don't need to give any of that, I can just tell you how it works. When executed well, hydraulic fracturing delivers just the right amount of energy to just the right place to fracture the rock in the best way to maximise gas or oil flow. Yep, you can frack an oil well too. It's been happening for about 50 years in the North Sea, and nobody cared about it until it came on shore. Of course, the most common application is in tight gas reservoirs, where very little gas would naturally flow into a well. These usually consist of shale, so we may drill a horizontal section through the reservoir. There are multiple methods of fracking, but in this case we may perforate one section, pump fracking fluid at high pressure through those perforations and fracture the rock. If we monitor how much fluid is leaking off and ground movement using seismic sensors, we can build up a picture of where fractures are occurring and to what extent. That way we won't accidentally fracture into, say, an aquifer and contaminate it. Speaking of that, contamination can occur from the reservoir itself, but also from that fracking fluid. If you're doing this in the UK, we're doing this in the UK, that fluid would be little more than water, biocide and sand. Biocide is basically bleach. We include that since bacteria getting into a reservoir can consume some of the hydrocarbon and produce toxic hydrogen sulfide. You may also choose to do an acid frack if the reservoir is limestone. There we pump acid to etch channels to the fractures, hopefully further increasing permeability. Acid frack sounds really scary, but honestly, the acid's consumed in the process. It's not as bad as it sounds. If you're doing this in America, Well, throw whatever you want in that fluid, apparently. Additives to reduce fluid viscosity are commonplace, and in some cases can be environmentally harmful, so definitely don't frack into an aquifer. Okay, what's the sand for? That is a proppant. It holds the fractures open when we reduce the pressure again. We then fire our next set of perforating charges, deploy an inflatable packet or something similar, and repeat, fracking the next section of the well. Hydraulic fracturing is something we've basically mastered over recent decades. Sure, it can go wrong, really wrong. But the phrase, things have gone a bit wrong, hits a bit different when nuclear explosives are involved. Oh, and hydraulic fracturing generally gives a higher gas yield than nuclear fracking. So from a commercial standpoint, the whole thing was a bit silly, really. But as I've hinted, the US tests went off without any recorded major injuries, fatalities, or serious safety incidents. If you insist on detonating a nuke down a gas well, Gasbuggy, Rollison, and Rio Blanco demonstrated about the best way of doing it thanks to good monitoring and adherence to safety standards. But I mentioned another country that tried out nuclear fracking. In their case, things went a bit wrong. As someone living in 2025 and looking back, one of the great joys of the Cold War was the unwritten rule that if America did something stupid, the Soviets were compelled to do the same thing, but bigger. The fact is, though this video focuses on US experiments, the majority of nuclear fracking attempts took place in the USSR. When the US announced Project Plowshare, the Soviets of course announced their bigger implementation with the catchy name, Nuclear Explosions for the National Economy. In fact, the Soviets were the first to attempt nuclear fracking. They performed it in an oil reservoir in the Grachevka oil field, starting off with two 2.3 kiloton bombs in 1965, followed with a 7.6 kiloton bomb and another pair of 2.3 kiloton bombs later in the field life. To their credit, the Soviets did actually share their results with the US engineers during a bilateral meeting in 1970, and the Americans traded their data with the Soviets. In fact, the Soviets went on to carry out nuclear fracking operations in 6 oil fields and 2 gas fields, giving a total of 25 detonations as far as I can make out. But, well, they didn't share everything. In the intervening years, and probably following the collapse of the USSR, information leaked out that things, in some cases, had gone a bit wrong. The surface equipment at the Griffin oil field was contaminated following drilling into the rubble chimney. It required decontamination, but without further study, I don't really know how severe that issue was. This 1996 report from the Lawrence Livermore National Lab, which is the main source for this chapter, states that groundwater contamination was still an issue then. In fact, they quote reports from Russian media stating that contamination had spread to 65 other wells in the field and threatened to contaminate the nearby Votkinsk reservoir, or even the Volga River in a worst-case scenario. Radiation levels up to 3 millirem per hour had been reported in some areas, and refineries had stopped accepting oil from the field. If that sounds like a bad outcome, here is a nightmare. Okay, another quick 2-sentence well engineering lesson. How do geophysicists detect oil reservoirs? One method is to detonate explosives at or near surface and measure the returning sound waves. By analysing them, it's possible to detect potential reservoirs. How about using nukes to do that? This was the Deep Seismic Sounding Project, another facet of the Soviets' Nuclear Explosions for the National Economy project. 4 of these explosions resulted in accidental and unplanned releases of radioactive material to atmosphere. The worst was the 1978 Kraton 3 test. In this case, the cement plug above the bomb failed and radioactive material spewed out from the emplacement hole uncontrolled. The world only really learned about this incident in the 1990s, and I don't really have the time to go into detail now, but it was a major event. Despite an urgent evacuation, nearby personnel received about 300 millisieverts of irradiation, which was about the annual permitted dose limit for workers. Airborne radioactive contamination was detectable in a plume that extended 31 kilometers from the site. And as for the site itself, 100% of the trees in this region were killed by radiation poisoning. Let's go and have a look at it on Google Maps. Oh god. Here is the dead forest. Still not grown back nearly 50 years later. The borehole was situated here, and this is a huge rock sarcophagus. The topsoil was removed and buried under this. That didn't stop radioactive contaminants leaking into the nearby water supply until the early 2000s. Imagine if nuclear fracking became the norm. Based on the accident rates in the oil and gas industry up until about the 1990s, scenes like this could have been commonplace. There is a second chapter to Soviets detonating nukes down wells, except this time, it was a unique success. There are caveats to that. Let's look at the situation. Remember back in the first chapter when I explained you can't just pump the drilling fluid out of a well while it's being drilled. The gas would flow uncontrolled to surface, otherwise known as a blowout. If you have a blowout, you've already failed so badly, and that is the first caveat. Though the Soviets didn't have red Adair, they were perfectly apt at dealing with blowouts. They had a lot of experience with them. There are a few methods to try and stop a blowout once it's occurred. In reality, a relief well is often necessary. This involves setting up a second rig nearby, drilling a new well that intersects with the first one, and pumping heavy kill fluid down at high pressure to restore wellbore pressure and keep the gas in the reservoir. A common question here is, why do they have to drill so deep? That looks like we're making things difficult. And the answer to that is, if we intersected at a shallow depth, we'd expose the shallower formation to reservoir pressure, fracture it, and that is how you create this. Unsurprisingly, steering the relief well to hit a target a few inches across is not easy. Once you're close enough, you can find the main well using magnetic sensors to detect the casing, but it's not surefire and still depends on getting within a few feet of the wellbore. So risky, difficult, and time-consuming. All while there's a raging torrent of oil and/or gas, which optionally may be on fire, and/or spewing out toxic hydrogen sulfide a few hundred feet away. And the actual intersection operation is risky. Get things wrong and you now have a blowout on the relief well in addition to the original well. I used to have a photo of a case where this happened, but I can't find it for the life of me now. Wouldn't things be a lot easier if we could just get near the wellbore? We can all see where this is going, can't we? Get close enough to the main wellbore, run a nuke down, detonate it. This turns the nearby rock to glass, crimps the well shut, and hopefully seals the blowout. I was always told the Soviets successfully stopped 4 blowouts using nuclear explosives, and the report from the last chapter all but confirms that. Of course, make of it what you will, it relies on Soviet data, so of course absolutely nothing went wrong. Though, when I worked in the industry, it was widely accepted and acknowledged that the Soviets did stop 4 blowouts using nukes. Ominously, I was also told they failed at a 5th attempt, and that is briefly mentioned in this report. And I think that's the other caveat to a nuclear relief well. In a desperate situation, it could honestly come across as a better option than nothing. Lazy tabloid newspapers published clickbait nonsense on the idea of using a nuke to stop the Macondo blowout back in 2010. That was such an ecological nightmare, yet so far from civilization, the argument could be made for risking a nuclear explosion to stop it. To be clear, it's not an argument I'd make. But what does the failure case look like? Once we actually think about this, a nuclear relief well comes across as more of a high-stakes gamble than a pragmatic use of nuclear explosives. If the explosive fails to seal the well, we could rather easily be in exactly the same position as before, but instead of a burning unstoppable torrent of natural gas, we'd have a burning unstoppable torrent of radioactive natural gas. And since a nuclear detonation is somewhat unpredictable, there's also the charming option of fracturing from one formation to another. That means contaminating an aquifer with radioactive material and hydrocarbons. Or we could even fracture up the back end of the cement to surface, making the blowout even worse. Not to mention all the risks of handling a nuke on the surface and placing it downhole are still present, but with the additional headache of time pressure that comes with drilling a relief well. I have no idea whether the Soviets' 5th failed nuclear relief well created a giant radioactive fountain, but based on their performance elsewhere, I wouldn't be surprised. Let's end this video with something that wasn't actually built, but was seriously proposed in this report as part of Project Plowshare. I begun with a reference to the fictional world of Solstice 5 and its unhindered resource extraction. Another part of that story was large-scale excavation and landscaping by some kind of gargantuan fictional energy weapon. Well, I suppose nuclear weapons are a gargantuan energy weapon. How about using them to excavate a sea canal? There are, of course, many obstacles to doing so, and so we'd want to do it somewhere relatively politically stable. A country that is relaxed and on good terms with its neighbours. Israel! Oh, why did it have to be Israel? Okay, This section's probably going to rustle a few jimmies, but I suppose if you don't want your jimmies rustled, don't commit a genocide. Enough. No further context, let's nuke Israel. Peacefully. So, this is a 1963 report from the Lawrence Livermore National Lab, which proposes nuking a sea canal through the Negev Desert in Israel. It is a legendary document. I have never read it before, so I thought it would be fun to finish this video off with me doing my first ever reading of the entire 2 pages of the plan that are presented here. I'll edit out the boring bits, but there won't be much to edit out. So let's get started. So the title of this document is The Use of Nuclear Explosives for the Excavation of a Sea Level Canal Across the Negev Desert in Israel Connecting the Mediterranean with the Gulf of Aqaba. Quite a lot going on there. Okay, so let's just begin. Another interesting application of nuclear excavation would be a sea level canal 160 miles long across Israel, connecting the Mediterranean with the Gulf of Aqaba, and thus the Red Sea and the Indian Ocean. Such a canal would be a strategically valuable alternate to the present Suez Canal, and would probably contribute greatly to the economic development of the surrounding area. The difference in elevation between sea level and the Dead Sea, 30 miles away and 1,286 feet below sea level, might also be used to generate hydroelectric power. Okay, I work for a company with quite a few hydro plants at the moment. I'm not sure how that happened. Would they fill up the Dead Sea and then what? Okay. Pump storage, maybe? Okay, that's a half-baked idea already. The maximum depth of excavation to be encountered is on the order of 1,500 feet. 500... Oh, God. That's 500 meters. Okay, so, right. Let's have a bit of context here. So, any civil engineering project, if you watch a construction site or a skyscraper going up, that kind of thing, you might notice they spend 1 year, 2 years doing basically nothing, and then the whole thing goes up in a few weeks. That's because earthworks are always by far the most complex and involved part. But shifting that amount of rock and earth is the most difficult part of any civil engineering project. The Panama Canal is quite possibly the largest civil engineering project of all time, for example. Conventional methods of excavation of this magnitude are prohibitively expensive, if indeed possible. Yeah, okay, yeah, that's what I was saying. But it appears that nuclear explosives could be profitably, okay, applied to this situation. Alright. Canal route. One possible route for such a canal across the Negev Desert has been sketched out in Figure 1. Figure 1, I'll get it on screen here, is a really poor quality sketch of 3 lines across the desert. It comes within a few miles of the Gaza Strip, by the way, just to float that one out there. Approximately 130 miles of the 160 mile length, 160 miles, of the route in virtually unpopulated desert wasteland. It'd definitely be unpopulated desert wasteland if they did what we're about to discuss here. And are thus amenable to nuclear excavation methods. Conventional methods could be used in the vicinity of the populated areas for an aggregate distance of 30 miles. These areas will also be the least difficult to excavate as they're fairly close to sea level. Okay, so that comes... Okay, 130 miles of nukes and 30 miles of conventional excavation. Okay. Okay, that's it, that's the plan. Okay, cool. Right, costs. In the absence of accurate profiles of the route and accurate information on the cost of mass-produced nuclear explosives, a very crude first approximation of costs of such a canal is given here. This is going to be fun, isn't it? Assuming, very roughly, an average cut of depth of 750 feet, that's 250 meters. This dimension controls and leads to a device spacing of 1,300 feet using 2 megaton devices buried at a depth of 1,300 feet. In order to get a channel width of 1,000 feet in rock. Okay, before we go on, right, okay. Right. So, Okay, so 400 2-megaton nuclear bombs, detonate them, blow out a canal. Imagine how that would look to aliens watching the Earth, by the way. What the hell are those guys doing down there? Anyway, okay, that might excavate a canal, I suppose. What happens to all the... Is ejector the right term? I'm not even sure. You've blown 400 holes, and now you've got... We're putting aside radioactivity, remember, it's the 1960s. Now you have all the material that's ejected just everywhere. That still needs to be moved? That still needs to go somewhere, right? What's happening with that? That's not going to be addressed here. I can tell that because we've got 2 more paragraphs left. So, I'm not sure how much of a problem this is going to solve. Why am I even reading through this? Okay, their projected overall cost for the entire thing is $500 million in 1963 money, so that's about $5 billion today. Oh, they have a 15% allowance for contingencies. The entire cost of this seems to be pretty much based on what I just said there, drilling the holes, in placing the nukes. There's no externalities, nothing else, but they do have a 15% allowance. I'd look for probably 2 orders of magnitude allowance on top of that. Why am I even... I'm not even going to bother critiquing that. Right, okay. Conclusion. The result of this crude preliminary investigation indicate that a sea level canal across Israel appears to be within the range of technical feasibility. It's It's more difficult to judge its economic feasibility. Another problem... Right. You know at high school or maybe at university when you have to do an assessment and you get told, make sure you consider the ethical and moral implications, and you know that just means stick a sentence on to make sure you're aware of it. That's how this report finishes. Another problem which has not been considered is that of political feasibility, as it's likely okay. As it's likely that the Arab countries surrounding Israel would object strongly to the construction of such a canal. That's the end of the report. I'll leave that last sentence as an exercise to the viewer. Normally, I finish these videos with a kind of nice conclusion that ties everything up in a bow. Honestly, this time, I have nothing further to add. Have a good day.